Thank you, Roland, for the introduction and also for the invitation. It's a pleasure for me to be here in Dortmund, and it doesn't look like the camera is working, but I hope at least you can hear me online. So while putting together the presentation for today, and also based on the discussions we have been having, okay, I'll just start. Okay, so I have been working on extreme meteorological events for a long time. Actually, ever since my PhD, and my PhD was 23 years ago. And over the time, I have worked both with heavy precipitation, drought, windstorms, heat waves, storm surges, and a wide range of others, also compound events, so to say, combination between events. But there was always one point in every one of the situations that we were that without something more than our physical understanding, there were ways that we could not come forward. So I have been using statistics, for bad or for worse, for 30 years now. And I have learned over this time that it is quite important also this exchange between disciplines. So on both sides, we can do better work, because often, like in this case, the expectation is that the result is more than the sum of its parts. And based on the discussions with Roland, so we've been working together in the Climate Stream now, and the expectation is that we develop new ideas for the future. I picked up a few examples for today, where you can then look at meteorological extreme events also from a statistical perspective. I have picked up windstorms as one of them. So this is from a satellite figure, and you see three storms one after the other. This is what we call the cyclone family, or example of cyclone clustering. And this had very specific impacts in reality. For example, a storm surge off the coast or broken trees. So because we also do a lot in terms of impacts. And if we think about heat waves, this is typically associated with a very big, we call it atmospheric blocking. I will show you later on what it is. It has a very local effect, and it's something that is very important now to map within cities the impact for the persons living there. And one way or the other, we cannot do this properly without using the right statistics to do. So the way I structured this is first a short introduction about climate modeling and climate change. Then I have a first longer chapter working, also half German, half English. So looking at windstorms and clustering. And then another one on heat waves, different metrics and storylines. So this is actually topics that I've been discussing with Roland and Merle for a while. And I will finish with a short takeaway messages. So I'm sure you've seen this type of time series often, also in the media, but I don't know if people really explain this often very well what this actually means. So this is actually real observations, and it is a time series that was put together from measurements since the late 18th century for Potsdam, Basel, Wien, and the Bild, which is in the Netherlands. And based on this instrumental measured data, we put together a time series where anomalies of annual temperature are recorded over this period. So 0 is the average between 1761 and 1970. So this is the 0. Every single year is one of the horizontal bars, and you have an 11-year running mean going through it. So, and additionally, you have, regarding this climatology, the different percentiles. And for a long time, not much seemed to be happening. So you have periods that are a bit warmer, a bit colder, you have a lot of variability. But it is clear that from the mid-20th century, something is starting to happen that is different. And particularly if you look at the last decade, all of these bars, or almost all of them, are beyond the 90th percentile of the previous climatology, even some of them beyond the 99th percentile. So it is very clear that the whole distribution is changing. And even more impressive, I think, is what we shown yesterday, below, sorry. This is something that we always update in our website, by the way, is that for every 25-year blocks over time, how many years were too warm or too cold? And here in the beginning, 18th century, 19th century, there is some variability. But it seems to be what we call natural variability. This completely changes in the 21st century, up to a point that on the 21st century, every year is too warm. All of them. There's not a single one that is too cold. And this is also what we always say to my students. This is one of the first slides I show them in an introduction to climatology. So it's not the fact that you had a hot summer or one extreme event that shows that you have climate change, but the fact that all of them are too hot. And for a statistician, this is very obvious to understand, but in terms of physics, there's people still that don't believe this is true. This said, it's quite important to say that such a clear long-term trend is not observed for other meteorological variables. You don't see this for annual precipitation. You see this for extreme precipitation, but not for total precipitation. And you also don't see it for windstorm activity. And this is one of the examples that I will show later. Okay, so by the way, you can stop me at any time if you have questions, either in German or English. I understand both. So first problem we have is that in the atmosphere and also in the other parts of the climate system, we are dealing with a very wide range of scales in which processes. So if I'm interested on wind gusts, I am looking at scales of minutes and let's say a few tens of meters. And if I am interested in trade winds and large-scale atmospheric circulation, I am talking about weeks to months and also thousands of kilometers. This said, if I have a perspective like this, like of the global atmospheric circulation, with all, so the trade winds are these winds here, the easterly winds close to the tropics. If I have this view of the world at these scales, it must be clear that the small scale processes are not or even very badly represented. And this is a general problem we have then in modeling. So when we transpose this to a climate model, so we make a grid, we use the basic laws of physics like conservation of energy, conservation of momentum, etc. And there's a lot of things that we can represent in this grid system. A lot of the processes just I mentioned are subscale and cannot be represented explicitly. This is why we use so-called parametrizations that give you things like convective precipitation, clouds, and radiation. So they are not explicitly computed by the model. You just want to know what is the total result of, let's say, the clouds in a 1-to-1 kilometer box to what is happening outside, because you cannot compute it for every single droplet. Obviously, this also makes a difference to what the models can show. And I will show an example for temperature. And actually, this is from a colleague from Helion, from a joint project. He made the example like, we have a very hot day, and what does it look like for my city in Hamburg? And if we pick up a global model, 150 kilometer resolution, this is the typical things you have in CMIP, you don't even see the city. So the squares are, as I said, 150 by 150 kilometers, you see nothing. If you go to regional climate model scales, 12 kilometers, you see a bit of structure, but you still don't see the city. It's only when you go to convective permitting scales, this so-called around 3 kilometers, that we can switch off a lot of these parameterizations that we have here to get much better results, in particular in terms of extremes. So this said, how extremes are represented in a climate model strongly depend on their resolution and on the parameterizations are switched on and off. And this is important for later on. Okay, so we start with the first example, which is an extratropical cyclone. So I'm not going to bore you with details how an extratropical cyclone develops. It's typically related with the westerlies that we have on the North Atlantic. Second. But I brought a figure, nevertheless, of a satellite image of such an extratropical cyclone. So here's the Iberian Peninsula. Here's Great Britain. So the core of this cyclone is, let's say, north of Ireland. Yeah. And associated with this cyclone, we have what we call a warm front and a cold front. This is what you see on the weather reports. And depending on the phenomena that you are interested in, the extremes will be somewhere else. For example, if you are interested in precipitation, probably you will be looking at what we call in meteorology the warm conveyor belt, which is this area where very warm air is pumped up upwards. And there is a lot of precipitation and a lot of latent heat release. So precipitation is probably maximum here. If you are interested in winds, probably the strongest winds you will get are associated with the cold conveyor belt, which is around the cold front and the core. So this is a scale of 2,000–3,000 kilometers. So to reduce a cyclone to the core, it can be that you are missing actually where the extremes are happening, because they might be thousands of kilometers away. Okay, this said, we then try to look in how far variability has changed of cyclones over the time. And for this example, what we are using is not direct measurements of wind speeds because they were not so good in previous times. We are using pressure measurements from which we can derive pressure differences, and from them you can derive the large-scale wind, the so-called geostrophic wind. Okay, so you have an information how strong the westerlies were. And if you do a time series and pick up a higher percentile of this time series, this is what you see above for the German Bight. You see this starts around 1900, goes until the last decade, and there is no trend. There are periods like the 90s that we had a lot of storms. There are periods like the 60s and 70s where we had fewer storms. This is also true for the last 20 years. But there is no sign of influence of climate change here. And the reason for this is for events like windstorms, this decadal variability is actually more important to any kind of signal. And I will tell you later on why. Okay. This variability is still very important. And this is something that we will put together through discussions with colleagues from the insurance industry around 15 years ago. What you see here is a list of events. This starts 1960 to go to 2010. So this is, so to say, the calendar years. Each line is 1 year. And this is the seasons from September to April. Each dot is one extreme event. And the color indicates you how strong it is. So if it's blue, it's strong. If it gets reddish and white, it's much weaker. And you can already see it's not really random what you see here. It's clear that you have a peak then over the winter, December, January, February. But if you look more closely, you'll identify a few periods that you have a lot of storms in a very short period of time compared to. And this corresponds to years like 1990, 1993, 1999, and 2007. And then this came also from discussions with colleagues in statistics, and we thought, well, let's try to understand what's happening. And actually, this is a problem that was known for a long time in meteorology, but nobody really tried to look at it from the statistical side until recently. So one slide with statistics for you, at least one, a very basic one. So the assumption that is doing here, and this comes from a formulation done by Patrick Mahler, which was a PhD student from David Stephenson, the colleague from Exeter that I mentioned earlier today. It just assumed that we could model the passage of cyclones over a certain location with as a point process. And we just assume if we have a constant rate, we can try to model randomness with this. And what if it is distributed the number of events per interval of time, then the expected value and the variance are the same, and the quotient of the two dispersion will be 1. We prefer to use what we call dispersion statistic and just take one thing. And the result is that if you have a value of 0, so the variance and the expected value are the same, you have a Poisson process, and you have this kind of distribution of data. If the variance is smaller than the mean, you have serial regularity. So it's much more determined when it happens. And if the variance is larger, you will start to see these groups, which is actually what we were interested in. And the clue here is that how can we relate this behavior to changes in the rate of occurrence? And in how far we can find the physical reasons for these changes. And this is what I would like to show you in the next slides. So this is something you already saw. So we see in a satellite picture, 3 storms, one after the other, going towards Great Britain. And as I said, this is something that if you have a bit of background in synoptic meteorology, like me, that it's actually an old hat, because the whole theory behind this goes back 100 years already. Because 100 years ago, colleagues from the so-called Norwegian school around Bjerknes developed this theory of cyclone families and how cyclones are related to each other. And if you look at the weather chart, and I will explain it more to you then in detail afterwards, you see that you have a number of cyclones, but they are linked together through their fronts. So from the physical side, this is something we already knew. We had just never really combined the two informations. And if we apply the dispersion statistic to the North Atlantic, we see, well, you don't see clustering everywhere. There is a region here on the core of the storm track where we have a lot of storms that we actually have a regular process. So every second day there's a cyclone going through there. And the clustering actually happens downstream, further east, or on the flanks of the storm track. So why does this happen? And this is what we're starting looking at. And one of the reasons for this, it has to do with the changes on the large-scale atmospheric circulation. So one of the main modes of variability of the North Atlantic, maybe you had this in school, I'm not sure, is the so-called North Atlantic oscillation. It basically gives you the strength of the westerlies over the North Atlantic. And if this is in a very positive phase, you have a lot of cyclones. This is what is shown here. So you have a lot of storms, and they will typically go here from the coast of North America towards the Arctic. If you are in the opposite phase, and again, please be aware this is not symmetrical. You have A, much less storms, and B, they are concentrated just over the central North Atlantic. Actually, typically in these conditions, you will have a high pressure center over Europe. So what you see below is a similar information. So the cyclone tracks that are just shown as a density below are shown as single tracks. Here is these red lines. The points of maximum intensity are in blue. And additionally to these, I have put the jet stream, which is the so-called westerly flow. And just imagine now we are in Newfoundland on the coast of North America. Depending on the phase, you will always have some cyclones there, independent of what the North Atlantic installation are doing. On the other hand, if you're in Iceland, this is a very different story. If you are in a positive phase, you will get a lot of cyclones. If the NIO phase changes, you will hardly get anything. So just because they're not these changes of patterns, it will already largely explain to you the figure that I showed you just before. There's another factor that comes on top of it, and this has to do with the fact that on the existing fronts of cyclones, new systems can develop. And this is something that, again, we already know for 100 years in terms of synoptic meteorology. And this is actually what is shown on the map that you have seen. That, for example, Storm Jürgen was associated with Storm Kirill. Kirill was 2007. It was the strongest storms we had in the 21st century here in Germany. And this was again linked to Lancelot a few days later. So these two reasons kind of give you the solution of the map that I just showed you. And now we come quickly back to insurance, just to give you a reason why this is important. I will just try to do some simple statistics. I actually did this originally just for give an example to some colleagues from an insurance company on the Netherlands. We have 60 years of data, and I just want to know what is distribution that from the 60 most intense events over time. Not the top one per year, but the top 60 of 60 years. And I just plotted the distribution. You already see here for the UK, we had very little storms in the 60s and a lot in the 90s afterwards. So this makes sense also to the graph that I showed before. This gets even a bit more extreme. If I show you just the top 12 events, so 5-year return periods, then it looks like for a few decades you had nothing. And then a lot of it happened here in the 90s. The colleague from the Netherlands was claiming, oh, Netherlands is such a small country, this doesn't play any role for us. And we just showed him it does. You see a lot of variability. And again, you can just have bad luck. And there's one of the cases, 1990, where they would have had 3 events in a single year. And this can be a huge problem because typically the way insurance companies work is that if you have a storm like Kirill, you buy coverage for that insurance. So if one happens, you're okay. If 2 happen, you're sitting in the costs. And if 3 happen on the same year, you can go bankrupt. And this is why even a small difference between a Poisson process and a cluster process can be very, very expensive in practical terms, and why the insurance was so interested in this. I now go back to a bit about climatology. This is basically the distribution of cyclones in the recent climate over the northern hemisphere. So the greener, the more cyclones. And if we look at the climate change signal, there is actually very little changes. So we know that we generally have less cyclones, particularly in the Mediterranean, we will have a lot more, but in the mid-latitudes, that's not much happening. And the reason for this, and I will not try to explain the next graphic in detail, don't worry, is that for a cyclone to attain a certain intensity, there's many different physical processes contributing for it. Some of them have to do with the temperature and the moisture in the atmosphere. These are related with precipitation, latent heat release. These become obviously more in a warmer climate. This is what is shown here. On the other hand, the pressure and the temperature gradients in the atmosphere are also going to change. And in the lower atmosphere, given that the Arctic is warming up much faster than the mid-latitudes, actually the temperature gradient between the pole and the mid-latitudes is decreasing. This means less potential energy can develop. So the total result of this is that we have a very complicated processes, but as a total, we have slightly less cyclones and they have more or less the same intensity. The only big change that we see is that given that we have a warmer climate, we will tend to see more precipitation associated with the cyclones, which is probably obvious to expect. But given that facts are counteracting each other, that you don't see a big signal. And this is probably also the reason why you don't see any long-term trend on time series. Also for clustering, and this is the first idea that I would like to throw to you. We looked at the climate model data, and they show some changes in clustering, but it's very heterogeneous. So the models show results, but they all show different things. The conclusion is that there is so much sampling uncertainty that we have actually no confidence on the results. So we don't know if it's a problem of the models or a problem of our statistics. But the truth is we cannot really estimate if there are changes of clustering, if any, for the future. Okay. I will now go to, am I doing in time? Just to make sure.
Perfectly fine.
Okay.
So, 30 minutes.
Yeah, so. Okay. So we now go to the next topic. Heat waves. And heat waves are associated with this type of, I will put the animation, it's easy for you to see, is that to have a windstorm, typically you have a strong westerly flow. For a heat wave, you have an interruption of this westerly flow. So you will have some kind of a very strong meridional flow that will let a big air mass on a certain location for several days, sometimes weeks. And over time, temperature will get higher and higher until you can get 30, 35, even 40 degrees. But it's a completely different atmospheric situation than what you will have an extreme windstorm. And this is what we call a blocking in meteorology. You can also just show it for this. This is in another case that we have the blocking, and below the blocking, you have the high temperatures. So they are kind of co-located with the blocking. If we look at the historical period, we don't really see changes in the frequency of blocking. On the other hand, we know that our summers have been getting warmer and warmer. So this is a distribution made for the last 500 years on anomalies of temperature over Central Europe, also with help of climate model simulations. And by far, the 5 warmest years were in the last 2 decades, or on the 21st century. Okay, so there also here you can already see there's something changing. The problem is, and this is one of the reasons why I was coming to discuss this with Roland and colleagues, it is very difficult to discern the changes in frequency, the changes in intensity, the changes of the area affected, and on the end, also on the time clustering. So here we see the changes, but it's difficult to assign the changes that we see to one of these parameters. And I will give you a few examples. First issue we have is with the metrics. So just like anything else, you can define the heat wave using different parameters. You can use them only using 2-meter temperature, which is easy. Or if you want to go to more impact-based research, like human comfort or heat stress, you can use other measures that also consider dew point, wind speed, and solar radiation in the end. Because the stress that we feel as humans does not only depend on temperature itself, but also on the humidity that you have. A PhD of ours a few years ago analyzed the historical time series and just compared what is the results that you get for these 4 indices. And well, they can be quite different. So I just brought an example, which is what is the maximum duration of a heat wave in a certain index for this historical period. And in all the cases, it was clear that it's mostly this so-called Russian heat wave that comes up, which is mostly covering the area, Russia and neighborhood countries. But, and now comes the details, the area affected is much different. And the length is very different, because for this Russo index, you come up maybe to 20 days in a fairly small area. And if you look at this index, the area is much longer and it goes up to 60 days. So it's very sensitive, the result that you get from the index that you are using. And then we made a comparison just for the top 5 events on this graph. This is what we call a bubble plot. I don't know if you've seen this before. And this is the information in terms of accumulated intensity. This is the information of duration. And the size of your bubble is how much area was affected. So it's kind of a 3-dimensional plot in 2 dimensions. And the colors indicate a single year. So red is 2010. So it is top 1 for the 4 indices. So the 4 of them are here. So for the sample that we had is the event with the largest area, the largest cumulative intensity, and the largest duration. Okay, so it's not that bad. But if you look at other years, they are very different. If you think about 2001, which is the blue one, the intensity is clearly lower than 2010, but the duration, for example, ranges from something like 12 days to at least 45. So you are dealing with a multidimensional problem that you cannot really tackle. And following up of this, Ines Dillerhoop, which is a PhD student now working on climate stream, she's been trying to take a closer look at this. And the idea is that it really depends on how you're looking at your data. So if you look this for a single grid cell perspective, so you're only interested in the grid point, this is actually very easy to do, because you just look how often your time series goes above a seasonal changing threshold, which is the red points, and then you can just put some conditions. And I say, okay, for this grid point, I have 3 periods that were over 3 days. This condition is filled in, so I would have 3 heat waves. The question is if this is meaningful looking at this for a grid point, because heat waves don't look like that. If we plot for a single day areas that fulfill these conditions, they might look like that. They have a part in Spain and France, then they have a part in Ireland and a part of Great Britain, and you don't know if they are together or not. A day later, it's more clear that they have something to do together. And then afterwards, this thing kind of disappeared from the British Isles and take a much broader effect of continental Europe. So the question is now that from this perspective, this can be seen as 3 heat waves, or can actually happen, this is only 1 heat wave, and just by chance, this grid point was on the border, and sometimes it's within that area and sometimes it's not. You cannot really see it by looking at a single grid point. So nevertheless, we try to put together a time series on heat waves for Europe, and of many of them we have. So for continental Europe, we have at least 2. So this means green. And every additional heat wave has a different color, and this adds to a certain area. Just to explain you the graphic. And actually, the years that we mentioned before, like 2003, is clearly top 1 in terms of area and in terms of the amount of events. The other ones are sometimes not so high. 2010 is a bit lower because the Russian heat wave is partially outside of the model domain, but there seems to be a more clear connection. And then we had the naive idea, let's try to see what this looks like clustering. And so the idea is we try to divide the time series in years that had a lot of heat waves, that had an average number of heat waves, or below average heat waves. And I will just put this in again. These are the 5 years that we were looking at. So 2003 is very clearly top 1, so a lot of heat waves. And the other ones, the solution is a bit more mixed. 2010 and 2022 are actually on the average side. And as I said, this really comes to the details. Because if you look now at the specific fields that contribute to this, they are very diverse, and this is what we would like them to discuss later. If you just count the number of heat waves per grid point, 2003 say, okay, we have a lot of heat waves here in southern France and northern Italy. Okay, so this is probably the reason why it's on the top. 2010 looks quite different. This has to do that the big heat wave was actually almost outside of the model domain. And 2021 and 22, they also don't look that spectacular. So the number of heat waves cannot be the main reason why these 2 years are on the top. So we can look at something else like temperature anomaly. Here you see other things. For example, that for 2021 and 2010, there were not the heat waves, but they were apparently very strong. And you can also look at another thing, which is the mean duration. And again, you see here that for 2003, there was a very long heat waves, but this is not necessarily, for example, the case for 22. And now we are back at the question. We are dealing with a multidimensional problem that we cannot really solve. Okay, and this is one of the ideas for the future. Very quickly to climate change. This is where I would like to show you the video, if it works. And I can explain to you what I'm showing you. So just imagine we take a real heat wave as it is, and we just put it in a different climatic background. So this is the heat wave from 2019 as it was. And here we put it in a background climate like 1850, and that one like the end of the 21st century. How we do it is yet not so important, but I just say the dynamics are the same. And if you look now at the heat wave, you see the huge difference that it makes, particularly at this part, in terms of impacts, if you are in the degree with about 1 day global warming, than if you are in a global warming that is 3 or 4 degrees. Coming back just to the summary, so this would be the situation just in the closed map. And this is the situation that you have in a 4 degree warmer world. And the interesting thing here is that the warming in a heat wave is much larger than the nominal global warming level. So in a 3-degree warmer world, the intensity of your heat wave might be 6 degrees more, and not 3 degrees more. And actually put some numbers here on the map for this heat wave. For example, we would have here on the present climate 40 degrees in Karlsruhe and about 36.5 degrees here in the Ruhrgebiet. And at 4 degrees, which is almost 3 degrees more than today, this will mean 45 degrees in Karlsruhe and 43 degrees here. And this is something that we can model directly with a model. We can really quantify very well these changes of intensity, and we know why. This largely has to do with drier soils that don't cool the atmosphere anymore and lead to even stronger heat waves. Now comes the problem. With this, we only, and this is my last slide with content, with this type of approach of the so-called storylines, we can only derive changes in terms of heat wave intensity. We cannot derive any changes for frequency of return periods. And this is one of the reasons why also in Climate Extreme, but another project, we have been trying to combine this information from the storylines with so-called flow analogs. Just imagine, you know what large-scale atmospheric circulation was associated with the event. For example, this flow chart that I showed you, this small movie. And I just look for a climate model and look at 100 of these cases in the present climate and 100 of these cases for the future, the closest ones that I can get. And I just look there. The heat wave that is produced by those cases, does the intensity change or not? And this is something we have been trying to develop, this combined strategy. It's a paper that is actually now also as a discussion online. And the idea is that through a combination of physically based methods and statistics, that we can derive both information of the changes of the magnitude and the changes of the return period, because only having one of them, it does bring us much further. And this will bring me to my very last slide. And I always have the feeling that we are working with similar problems, but from very different perspectives. So on my side, meteorology and climate science, and in your case, maths and statistics. And real progress also from my experience in the past, that this combination of these disciplines can be extremely helpful in order to move further to understand how extreme events can change in a warmer climate. And again, I hope I could motivate it a bit by showing you examples where we, with our physical processes, really kind of reach our limits of what we can do. Okay, that's it for today.